So now we come and actually go through the astronomy and physics use cases, all of which are pretty large data. So the first one comes from Caltech astronomer, who is part of a collaboration which runs the Catalina Real-Time Transient Survey. And this is basically looking at the large region of the sky in this case, in the visible light regime, or wavelength, to look for things that are changing, and then to go and find those things that are changing and looking at them in more detail. So this finds supernovas, variable stars, black hole type activities, then the jets that those produce, stars that actually have an unusually large amount of motion. And the information comes from 3 telescopes, 2 in Arizona and 1 in Australia, and they're adding 1 in the near future in Chile. So on a clear night, it generates a tenth of a terabyte of data, and it has about 100 terabytes so far. They're pre-processed at the telescope and transferred to Arizona and Caltech for further analysis, distribution, and archiving. This data is deliberately processed in real time, so that transient events are published electronically through a variety of mechanisms without any, there's no withholding period. Sometimes in science, you allow the person who took the data some special time where they look at the data only. This is not true here. Here, the data is made available immediately because it's not necessarily so that the actual people running the survey are the right people to exploit a particular transient event. So then the later data analysis classifies the transients, does the additional observation using other telescopes, interprets it scientifically, and publishes it, of course. It uses archival data to compare their observations with. It's a wide variety of geographically distributed sources from the so-called Virtual Observatory Framework. Astronomy was one of the very first fields to set up a so-called the virtual organization attached to them, and that virtual observatory is highly successful. It has machine learning in the classification, streaming data, pleasingly parallel type processing of the individual events, and then parallelism both over images and then later parallelism over events. And these events are identified in telescope images. This is not a future project, it's a current project. However, it's a precursor of a very famous project, the Large Synoptic Survey Telescope, LSST, which is meant to operate in the early 2020s as a very high priority instrument, astronomy, and has a sort of process to decide what the field wants to do. And LST will take that 0.1 terabyte and make it about 30 terabytes per night. This slide here shows the actual classification process. You have the input data coming along from the left. It pops into here. It compares with existing data, either from the survey itself or other resources. That classifies it into events. Then you have these machine learning and expert system type ways of identifying the type of event, gives you probabilities for what the event is, and then you go and do follow-up scientific work, follow-up data analysis, take two new images, point a specialized instrument at it, and so on. So this slide here basically says in words what I already told you orally about the previous picture. It tells you how that architecture is the cyber infrastructure for a general approach to time domain astronomy, and how the various things such as the portfolio information, the machine learning, and everything is used. And critical is that these events are generated and processed in real time. And an interesting feature of this whole field is, why does astronomy have big data? Because actually the telescopes are not a great deal bigger than they used to be. What's happened is the cameras are much better than they used to be. So you get many more pixels than you used to do, because the size of telescope is limited by atmospheric and physical construction principles. This describes the classification of this application. It has the basic parallelism over celestial objects. It runs the filters, which are the machine learning for further study, and generates events. Events themselves are parallel because there are a lot of events. And so you have, but that could, of course, a much smaller number of events than original objects. So this is a good example of a streaming application. The data is clearly being generated in real time, and it's critical to have a classification because you want to actually identify interesting events, which means you must classify all the cases where things are changing. Here's further, we have next two use cases add to this case here. Then this one here, it notes that we can effectively take these types of data we're discussing and integrate it with simulation. We can actually do that in all fields. And in fact, there are many use cases in different fields which do this integration. And then the simulation is typically run on a high performance computer, but the data analysis is usually appropriate for a cloud. So this extreme data application discusses various future astronomical instruments. There is the Dark Energy Survey that's covered in the next use case. There's the Wiki Transient Factory, which is a petabyte per year. That's actually implemented on the old Mount Panama telescope in California. The LSST we've already discussed, which is 7 petabytes a year coming, and this is more optimistic than the previous early 2020s. So let's say it's 7 petabytes a year whenever it happens. And the simulations already, they think, will be 10 petabytes of output from the simulations in 2017 from maybe 200 million hours of supercomputer time. Notice this little picture of the LSST. It's got a 3.2 gigapixel camera and a picture taken every 20 seconds. So that's a lot of pixels on this one camera. I told you, telescopes have changed due to the cameras, not so much due to the telescope sizes. Here we have the Dark Energy Survey. Here the data comes from telescope in Chile, and then it goes from Chile to NCSA and also to Lawrence Berkeley Lab for storage and also for processing. And the galaxies and stars and the various images and surveys which compare images are cataloged, and their properties are measured and stored in a database. And again, this is using looking for transients through machine learning algorithms which identify particular changes and map them into transients. It uses, this one is still using Oracle databases, large memory machines, GPFS, the standard HPC, one of the standard HPC file systems. This also is using Python type wrappers, as I mentioned, are very common. They need in their machine learning large-scale Cholesky decomposition techniques, which correspond to matrices of 1 million elements on a side, and they would need to also be able to store images in parallel. The LSST will be particularly challenging in this regard. And here's an example of the Dark Energy Survey in Chile with this new, yet again, a new camera being installed. Now we come to the particle physics example. We have the standard picture of, which is of course not a real picture because it's really showing things underground. It superimposes on the map of the link between France and Switzerland. This actually crosses the border. It has, we have here the initial acceleration is done here. The protons and antiprotons are then injected into these rings, and they're collided at various places. You can see where the rings cross for the protons and antiprotons. 1, 2, 3, 4. And these are the halls where the different experiments. We see CMS Atlas, which are the two general purpose experiments, LHCb and Alice, which are more special purpose and somewhat smaller data sizes. So now we note here that there's 27 kilometers around this ring, and it's actually at the depth of 175 meters at its deepest. So the data is the collisions happen here along at these sites here. There are these huge apparati which are giant by any reasonable standards, which take the data, they record the results of the collisions. That data is written out to disk. It's analyzed by a special large local cluster to select the more interesting events, and those more interesting events go on for detailed analysis. These are huge examples of global science. Namely, CMS, one of the two general purpose experiments. The other is, of course, Atlas. Has 3,600 participants, 183 institutions in 38 countries. Wow, that's. I used to work in this field. We had 30 people in our experiment, and I found that pretty big. And one of the reasons I left that field is I thought working with 30 people was not so easy. But now they have 3,600 people, so obviously I was a bit impetuous in those days. So this now goes a little more detail in the actual analysis. So we have to analyze this data. That's done through one of the major resources is the LHC grid, which has 350,000 cores running and 2 million jobs per day. The LHC analysis is organized into these three tiers, which are basically CERN is sort of tier 0. Tier 1 is sort of in the country. Tier 1 in the US is a Fermilab in Illinois, and there's a tier 1 in 3 other places in Europe, and then lots and lots of tier 2s, and then tier 3 is basically your local workstation. We have around 15 petabytes of data and 200 petabytes, 15 petabytes of data per year, 200 petabytes total. And here's some data about Atlas experiment in 2012 at 8 petabytes of tape, 10 petabytes of tier 1 disk. And I guess actually this slide here about the US tier 1s is not correct. It misses out some. There is a tier 1 also at Brookhaven. And tier 2 centers have 12 petabytes in total. And this is just one experiment, Atlas. CMS has a similar architecture and similar sizes. Notice that this information again involves not just raw data, it also involves simulations which are used to be able to analyze understand the data analysis and quantify the errors in that analysis. And there's almost an equal amount of data from Monte Carlo, which are the simulations that there are from the real experiment. So it points out here that the accelerators are increasing in power, but the Moore's law is sort of slowed down and has now become core law, not speed law, and so that requires new challenges. And there's also the usual issue of power consumption and so on. I would say that it's not so obvious to me that this field is not as challenged as some other fields because they can just increase the size of the number of cores, and maybe they can even do some quicker pre-analysis to be able to isolate those events that need the full analysis. And they certainly probably do need to reload. I mean, the software, the planning for the software for this discovery of the Higgs happened 10 years before the actual Higgs was discovered. So this is a huge effort. At every stage, large-scale testing is being done. So, and I think in the future, clouds will turn out to be particularly important because they are naturally supporting this type of application. Whether you can actually afford to do it on commercial clouds or you really need these sort of 3 cycles from physics clusters is not so clear. Now we come to use case 40, the high energy physics experiment, BEL-2. This is only involves 400 physicists and engineers. It's in Japan at Tsukuba, and whereas LHC is accelerating protons and antiprotons, this is accelerating positrons and electrons, the antiparticles, of course, of each other. And when E plus and E minus collide, they, among other things, can be run at an energy where they have a very enhanced production of the B meson. The B meson is made from a B quark combined with conventional quarks, U bar and D bar, up and down quarks in the antiparticles. And it has very high intensity because it's very specialized and optimized for this particular. It's nowhere near the total energy of the LHC, but and also because of that, the data analysis is somewhat simpler because fewer particles are produced, but it has to be done highly accurately because they're looking at small effects called CP violation, which is a very subtle effect in the interaction between the particles of high energy physics. So this is currently running the BEL accelerator. This will become BEL-2 with an upgrade. And that starts in 2015 with a factor of 50 increased data. They expect to get 120 petabytes. And actually here we see the Monte Carlo ratio is 100 petabytes to 15 petabytes of physics data. They want to be able to take the data in Japan and basically transfer it continuously to the US. And they have, there in the US, they will use the so-called Open Science Grid, GN4 and Dirac and FDS and BEL-2 are pieces of software. And this has, what is its characteristics is MR-stat, because that's the way when you do physics analysis, you're doing large-scale statistics, histograms, that's MR-stat. Parallel PP, pleasingly parallel processing, that's because each event is processed on its own. Well, Monte Carlo MC, that's the Monte Carlo data. We notice that's 6 times as big as the actual raw data, and the parallelism is over collisions, whether those collisions be real collisions or simulated collisions.